December 21st, the darkest day in the northern hemisphere on Earth. Daylight is minimal, with the North Pole not receiving a single trace of light from the electromagnetic spectrum of the sun. Nothing is detectable. Just 6 months earlier, however, June 21st, the scene is vastly different. The longest day. The sun never sets at the North Pole. Imagine it. A bird arrives at the North Pole without ceremony. Not because the journey was small, it crossed hemispheres, seasons, storms, but because here nothing announced his arrival. There are no trees to break the sky, no cliffs to name direction, only light, spread evenly, like breath held too long. It circles low. To human eyes, the world is white, and blue, and silver. Ice stitched to ice, sea breathing through cracks, the sky washed thin as if someone diluted it. But the bird does not see what you see. The ice is not white. It is veined. Under ultraviolet light, the frozen sea fractures into patterns. Pale violet seams where pressure meets pressure. Faint dark scars where yesterday's cracks refroze. Old ice glows differently than new ice. They can tell which floes will hold its weight, and which floes will sigh open by evening. The water is not blue. It is black. A mirror that eats UV and gives nothing back. Fish betray themselves here. Flashes of UV reflection from scales just beneath the surface, brief as a thought. The sky is not empty. It is textured. Gradients of polarization and ultraviolet brightness that form a map no compass could replace. The bird knows where it is, not by landmarks, but by how the light leans. Feathers on his own wings shimmer with patterns. Signals meant for others like it. Proof of health. Proof of endurance. Proof that the long flight mattered. In a place without flowers, without root life, it is alive with light, humming with information. The light is structure. The light is memory. At the top of the world on the longest day, the bird sees a version of the earth that human eyes cannot. A planet stitched together by wavelengths we've evolved to ignore. Parts of the light we cannot see. Imagine a world where we possess the receptors to sense the environment like this bird and other animals. UV receptors to detect ultraviolet light. Polarized light receptors to guide the way home like ants. Echolocation receptors to orient in space without sight. Better yet, imagine a world where we have receptors not yet imagined, to interact with the world in ways we have not yet conceived. The receptors we do have send information to our brains through circuits of neurons that ultimately project to sensory areas of the brain. S1, the primary somatosensory cortex, is responsible for touch. A1, the primary auditory cortex, is responsible for hearing. V1, the primary visual cortex, is responsible for sight, and there are many others. As we develop from infancy, when we encounter a tactile, auditory, or visual stimulus, neurons in these regions of the brain begin to fire, strengthening their connections and molding our cortices into what we will go on to use for the rest of our lives. Each sensory region also contains a map of that modality. We have a touch map of locations of the body in the somatosensory cortex. We have a tonal map of different frequencies in the auditory cortex. We have a map of our visual field in the visual cortex that corresponds to a similar map on our retinas. Our current maps of touch, tone, and visual space orient by location, such that there is a location on S1 dedicated to each finger, to each toe, to each part of the body, with regions of the body with more specialized uses occupying more space. These maps are refined by genetic variation and can be refined by use. If novel receptors emerge naturally, they might take over our current sensory cortices to process information and integrate it into the brain. For example, if a human is born without functional photoreceptors and is blind, the visual cortex is surprisingly taken up by connections to neurons dedicated to other senses. This human, in a sense, will have high acuity for other senses and more brain areas dedicated to other tasks. The visual cortex will still be used, but it will now respond to sound, to touch, and to other senses. Multimodal areas of the brain, regions that correspond to more than one sense, integrate signals to help us construct a coherent model of the world. A classic example is the superior colliculus, which contains aligned maps of both the visual and auditory space. Neurons in the superior colliculus respond to where something is seen and where it is heard, allowing these signals to be compared and combined. We localize sound by detecting small differences in the timing and intensity of sound waves reaching the left and right ears, which are transformed into a spatial representation that converges with visual input in the superior colliculus. Likewise, depth perception and vision emerges from integrating slightly offset images from the two eyes into a single three-dimensional perception. This raises a broader question. If perception itself is fundamentally about integration, what other dimensions of the world could we in principle sense using the receptors we already have if the brain learned to combine their signals in new ways? As with a bird's ultraviolet sensory receptors, the emergence of a new sense would not necessarily require an entirely new receptor type or cortical region. Instead, it might arise from a new mode of integration of existing signals. In fact, we already possess access to many such signals, but they're invisible to conscious perception and would require specialized systems, biological or technological, to detect and interpret them. Here are some possibilities. Downstream consequence receptors. Receptors that allow one to feel the downstream consequence of reactions, where touching or encountering an object conveys not just its physical properties, but the trajectories it tends to set in motion. What if touching something didn't just tell you what it is, but what it tends to cause? Actions such as kindness, neglect, or violence might carry immediate trajectory sensations, forming the basis of sensory ethics. We know that experiences are written into the body through chromatin and epigenetic modifications. Perhaps there could exist a mechanism, biological or augmented, that detects when such chromatin modifications are actively being written, allowing consequences to be sensed as they form. It could be felt the same way heat or pressure are felt. Temporal density receptors. While time is often described as the fourth dimension, what if we could sense time as a terrain rather than a clock? We know that biological time is tracked through epigenetic clocks associated with aging and chromatin states. We know that time is also tracked in the suprachiasmatic nucleus of the hypothalamus. But what if temporal dynamics could be measured in real time, allowing a direct perception of how dense, stretched, or fragmented a moment is? Trauma might register as jagged, fractured temporal landscapes, while creative flow might feel like moving through thickened time, wading through syrup. Number 3, interstate externalization receptors. Mechanisms that allow internal mental states to become perceptible, where emotions, intentions, or cognitive states appear as visible or spatially extended phenomena. Rather than introspection alone, this would allow the mind to be seen, turning subjective states into observable features of one's perceptual world. We are constantly searching for new signals. The universe is not silent. We are only just beginning to see the unseen as real, gaining missing dimensions of apprehension. We live in a world saturated with signal, but lack the receptors, coincident detectors, and interpreters to understand it.